Hello friends, this is third week's lecture of Probability and Statistics course. We continue from page 21, example 2.15. Let's start. A university warehouse has received a shipment of 25 printers, of which 10 are laser. And 15 are inkjet printers. If 6 of those 25 are selected at random, select 6 of them, to be checked by a particular technician, what is the probability that exactly 3 of these selected are laser printers? Exactly 3 laser means 3 laser plus 3 inkjet. Okay, this is part A of the question. And second part of the question asks at least 3 inkjet printers. At least 3 inkjet means 3 inkjet and 3 laser, and 4 inkjet and 2 laser, and 5 inkjet and 1 laser, and 6 inkjet. Yes. Let's start with part A. 3 laser and 3 inkjet. Yes. Laser, we have 10 lasers. In how many ways can we select 3 laser? 10 combination with 3 and 15 combination with 3 inkjets over sample space. Yes, in total, among 25 printers, we are selecting 6 of them. And part B of the question, yes, it includes 1, 2, 3, 4 different combinations. Let's start with 3 inkjet. Inkjet is 15, you see. 15, 3, 10, 3, plus 4 inkjet, and 2 laser, plus 5 inkjet and 1 laser, plus 6 inkjet. I don't have to write 0 laser here, but if you write, it corresponds to what? 1. So it doesn't change our solution. Over, what is the common denominator? It is the same, 25 combination 6. Yes, the solution may take some time, but it is given in your book as you see. Any problem about this? Did you understand? Yes, Abdu. Thanks for your solution. And partitions. The number of ways of partitioning n distinct objects into k groups containing n1, n2, nk objects respectively is n factorial over n1 factorial, n2 factorial, nk factorial. Here, the total the sum of the numbers in the denominator must be equal to n. Simply. To understand this, let's have a look at the example. Consider 10 engineers to be split into 3 groups. 10 engineers to be split into 3 groups to be assigned to 3 different plants. If we are to send 5 people to plant A, 3 people to plant B, and 2 people to plant C, this is a partitioning problem as you see, then the total number of assignments, that means in how many ways, is equal to n factorial over 5 factorial, 3 factorial, 2 factorial. As you see, if we had partitioned it to 2 different groups, we would obtain combination, right? For example, we have 10 engineers, 7 and 3 to 2 different plants, 10 factorial over 7 factorial, 3 factorial. Yes. So this is a general expression, and combination rule is a specific expression derived from this general one. Okay? Did you understand it? Yes. Let's continue with the exercises. An incoming lot of silicon wafers is to be inspected. For defectives by an engineer in a microchip manufacturing plant. Suppose that in a tray containing 20 wafers, 4 are defective. Yes, we have 4 defective among how many? 20. So 16 are non-defective. Yes. 2 wafers are to be selected randomly for inspection. So we select 2 of them. Find the probability that neither, what does it mean? None is defective. Yes, none of them are defective. So we select the 2 among non-defectives. In how many ways can you select 2 silicon wafers among 16 non-defectives? But our sample space is what? What is my sample space here? Yes, 20 combination 2 is my sample space. Okay. The next question, a person draws 5 cards from a shuffled pack of 52. Again, we have a card question. Select 5 cards. Among 52. Find the probability that the person has at least 3 aces. Yes. At least 3 aces means 3 aces and 2 others. Okay, non-aces. Let's say 2 non-aces. Okay, but at least 3 aces. So it means and 4 aces plus 1 non-aces and 5 aces. Okay, do you agree with me? Yes, no, yes, no, yes, no. Yes, but there's a problem here. Yes, Mehmet Emre recognized it. Yes, we have how many aces in total? Yes, there are only 4 aces, so we don't have such a choice. So the first two ones, 3 aces from 4. This is part A of the question. 3 aces from 4. And the other 2 cards are from what? From what? Non-aces. I mean, what are non-aces? All the cards here. Yes, for the 8. For the 8, combination 2. And we have another. Before dividing it to sample space, let's write the second one. Among 4 aces, we select all. There is only one way for it, you know. And among 48 others, we select one. It has 48 different ways, you know. Over our sample space is, like Abdo has written, 52 to 5. Yes. This is part A of the question. We have also part B for it. Find the probability that the person has at least 4 cards of the same suite. At least 4 cards of the same suite. What is a suite? I think you know what is a suite. Each row is a suite. This is a suite. This is a suite. This is a suite. This is a suite. We have 4 suites. Uh, let's have an approach that, for example, let's start with making a combination that all the cards, no, at least 4 cards are from this suite. I don't know the name of it, but I know the name of hearts. Let's select it. At least 4 hearts. Let's solve the question for this, and then we can multiply it with 4. We have 4 suites, you know. But in the beginning, let's solve the question for only hearts. At least 4 hearts. You know, there are 13 hearts. Yes, 13 hearts. And non-hearts are 39. One from the others. These are hearts. 13 are hearts. And 39 are others. Okay? And this is one combination plus at least 4 hearts. This is only exactly 4 hearts. Let's also add 5 hearts. Pardon. 13 combination 5. And 0 from 39. We don't have to write it, you know. Over sample space. Over sample space. Yes, this solution is for what? This solution is for only hearts. I solve the question as the question asks me find the probability that the person has at least 4 cards from hearts. Yes, but it asks me of the same suite. Of the same suite means each suite satisfies the condition. So I multiply this solution with 4. Okay? Do you agree? It's okay? Yes. So let's continue. Ali Osman, I also don't know names of some suites, for example. I am not good at it. But in probability course, we generally deal with cards and the basic information is sufficient. What is the basic information? There are 52 cards. We have 52 cards consisting of 4 suites. Each suite consists of 13 cards. Okay, and each suite is from 1 to 13. 1 is denoted as ace. This is 1. 1 is ace. After 10, they use letters joker, queen, and king. That's all. We don't use more sophisticated questions. Okay, this knowledge is sufficient. Club, let's write club, hearts, spades. No, this is hearts. What is the first one? The first one is clubs. Okay, spades, hearts, diamonds. Okay, that's all. Yes. Next question. Three people enter the elevator on the basement level. Basement level. The building has 7 floors. There is a basement level and we have 7 floors. Floor 1, 2, 3, 4, 5, 6, and 7. We enter the elevator, or 3 people enter the elevator at the basement level. The building has 7 floors. Find the probability that all three get off at different floors, not at the same floor. None of them exit at the same floor. Yes, what is your approach to solve this question? How should we solve it? You don't have to use combinations here. I mean, no. That's also possible, Mustafa. Find the probability of same floor, but we should subtract all of them exits in the same floor or two of them exits, combinations of two of them exits in the same floor and so on. It is difficult. The correct approach should be the first one has 7 floors to exit. The first one has 7 floors to exit. The second one has 6 floors other than the first one. And the other one has 5 different choices other than the first two. Okay? This is a number of what? Different choices or different combinations. And over the sample space, yes, Ahmed is right. My sample space is 7 times 7 times 7 because in the sample space there is no constraint. All three can get off at each floor. They have each 7 choices. So this is my sample space, okay? And the favorable outcome says the first one can exit in 7 different floors, the second one 6 choices, the third one 5 choices, other than the first two. Okay? Any problem? Any problem about it? Can we solve it with combination? Combination. Let me check it. If there is a solution with combination, it is not trivial, I think. Not very simple. Yes. It would not be the best choice, I think. I cannot see a solution with combination now. Yes, so let's continue with 21st question. In a group of 7 people, each person shakes hands with every other person. How many handshakes did occur? Here, the main question, the area of concern is, does the order matters? Yes, if order matters, we use permutation. If order doesn't matter, we use combination. So let me ask you, we have a group of 7 people. Person A handshakes with person B. After then, do we expect B will also handshake with A? Or will they handshake twice? No. Yes. No. They will not handshake twice. So this is a two-way relation. So order does not matter. So what does it mean? Combination. 7 combination 2 is the solution for this question. Yes, we have a good question now, a bit it may be a bit difficult, not too much. In a lottery, 6 numbers are drawn out of 45. Yes. You hit a jackpot if you guess all 6 numbers correctly and get $400 if you guess 5 numbers correctly. So we have two parts for this question. Guess 6 numbers correctly and guess 5 numbers correctly. What are the probabilities? Yes, not in how many ways. This is a probability question, so you will divide it with sample space. Yes, I wait for your suggestions. How can we solve it? Part A. Six numbers are drawn out of 45. You hit a jackpot if you guess all 6 numbers correctly. What is the probability? Abdul, do you mean dividing or any combination? Mohammed, 45, 44, 42, 43, 42, 41, 40. I don't know, it corresponds to the same solution with me. Let's check it while solving. Yes, any other suggestions? Oh, you mean 6 over 45? No. No. Not so simple. Yes, any suggestions? One over 5 times 45. No. No. Not combination. Mohammed, I will check your solution with mine if it is true. Yes, any other suggestions? Combination 6 with 6 over. Yes, Abdo is right. Abdo is right. Ali Osman is also close, but Abdo gives the correct solution. How? Let me explain. Yes, in a lottery, you write 6 numbers to a card. For example, you write 5, 11, 19, 25, 32, 40. You write it to a card and register it to the office. Give it. At night, they draw 6 numbers. For example, they are correct numbers. For example, they draw, for example, 5, 10, 19, 20, 32, 40. These are correct numbers. At night, they draw 6 correct numbers. And you check which one match the correct numbers. These matches. You have 4. Yeah, what is the probability? What is the probability? After the night, after the draw, after is important here. After the draw, we have 6 correct and what? 39 non-correct numbers. Okay, and our question turns into what is the probability that you select 6 numbers, those are all from the correct ones. Select 6 numbers from corrects. 6 combination 6 over what is the sample space? Sample space here is 45 combination 6. This is my sample space. This is my favorable outcome. Okay. So Abdo is right here. And part B of the question, 5 numbers. Yes, 5 numbers correctly. This was part A. And part B, order doesn't matter. No. Part B, 5 numbers correctly. 5 numbers from corrects. 1 number from non-corrects. That means 5 number from 6 corrects, 1 number from 39 non-corrects over sample space. Okay. Order doesn't matter because, for example, this is the correct order, but you write 19, 25, 10, 40, 32. This is also correct. So order doesn't matter. Is it okay, friends? Okay. If a group consists of 8 men and 6 women, in how many ways can a committee of 5 be selected? 8 men, 6 women. In how many ways can a committee of 5 select 5 be selected if? Let's solve part A and C. The committee is to consist of 3 men and 2 women. 3 men means 3 from 8, 2 women from 6 over 14 combination 5. And part C, there must be at least 1 man. At least 1 man. In how many ways? In how many ways question. So you don't have to divide it to sample space. Ways. Yes, this is the number of ways. We don't have to divide it to sample space. In how many ways can you select the committee of 5 if there must be at least 1 man? At least 1 man means means 1 man, 2 men, 1 man and 4 women, 2 men and 3 women, 3 men and 2 women, 4 men and 1 woman, and 5 men. It is a long way to solve the question. It is the complement of no man, right? At least 1 man is the complement of no man. So here we can find it by sample space minus no man combinations. Yes. Here, what is my sample space? We select 5 from 14. We select 5 people from 14 minus no man. All of them are women. 5, a committee of 5 from 6 women. And no man. How many men do we have? 8 men. 8 men. 0 from 8 men. Okay. So this means all women, and this is sample space, okay, gives us at least 1 man. Up to if it was a probability, we should subtract it from 1. But since this is a how many ways question, we should subtract it from sample space. Okay? Did you get the difference? Let me repeat, it is important. If the question is a probability question, if it was a probability question, you should subtract from 1 the probability. Okay? But since this is a how many ways, number of combinations question, I subtract it from sample space. Okay? So let's have a break. Let's continue after 10 minutes. Yes, friends, let's continue. Can you see my screen and hear my voice? Good. From a box containing 5 chocolates, and 4 candies, a child takes a handful of 4. Select 4 of them. What is the probability? This is a probability question. Exactly 3 of the 4 are chocolates. 3 chocolates from 5. 1 from 4 candies over 4 chocolates from 9. As you guessed, this is a simple question. Yes. And Pascal triangle. Do you remember it? Yes, it is simple to construct a Pascal triangle, as you remember. You start with a 1, 1 and 1. Yes. The sum of 1 and 1 gives you 2. 2 and 1 gives you 3. 2 and 1, 3. Yes, the sides are equal to 1 always. Also 1, 1, 4, 6, 4, 1, and so on. Yes, this is, for example, this is the 4th row. In fact, the 5th row, but we don't take into account the top of the pyramid. So this is the 1st, 2nd, 3rd, and 4th rows, and these are the combinations of 4. What combinations? 4 combination 0, 4 combination 1, 4 combination 2, 3, and 4. And this is called as binomial distribution that we'll see the details later. Okay. Here, for example, the 10th row. For example, you wonder what is 10 combination 3. This is 10 combination 1, 10 combination 0, 1, 2, 3. Yes, is 120 from the Pascal triangle. Yes, again we have a simple and a good question, high quality question. The first one is simple. A drawer contains 3 white and 2 brown socks. 3 white and 2 brown socks. 2 socks are selected at random. What is the probability that you got 2 socks of the same color? Same color. That means 2 white or 2 black. This is a probability question. Probability question. So the probability of 2 white is this. I don't write this 0. Black 0 from black's combination. I don't have to write. This is the white combination and this is the black combination over sample space. It is 5 socks and 2. Yes. The first part, the first part corresponds to 2 whites and the second part corresponds to 2 brown socks. Okay? Yes, and I know that there are both computer engineering and electronics students here, right? Are there? I know, yes, this is a computer engineering class in the origin, but we combined electronics class also, so there should be electrical engineering students also. Are there? Perhaps half of you. Today we have a high quality cryptology concerning not mainly concerning computer engineering questions. Here, this question is a cryptology based question, and also we will solve a electronics and communications based question later in the coming pages. Let's start with this cryptology question. For password security, it is often recommended that users choose passwords that contain at least 2 digits, some capital, etc. This is an example, not exactly a question. This is an example, okay? You know, when you are selecting a password, you are asked to use uppercase, lowercase, digits, special characters, etc. This is to improve the security of your password, level of security. Calculate and compare the available number of passwords. Yes, this is available number in how many ways question. When using the following conditions. A 6-letter password. Yes, in all of the questions, all parts, we will generate a 6-character password, okay? A 6-letter password only consisting of lowercase letters. In how many ways? Here I have to give you some hints. About what? In English alphabet, yes, you can use the same letter. For example, you can select a password as A, B, B, B. This is valid for part A. Okay. I have to give you the conditions for this question that in English alphabet we have 26 lowercase letters. Also 26 capitals. In addition, we have 10 digits. Yes, this is okay for this question. We only need these numbers. Let's start with part A. A 6-letter password only consisting of lowercase letters. You can use a letter twice, 3 times, 4 times, etc. You are free. So, you will only use lowercase letters for a 6-character password. In how many ways? Yes, Mustafa Esat is right here. Our solution is 26 power 6. Okay. Why? Because you have 26 combinations for all digits. Okay. So our answer for this question is 26 power 6. Ve part B says a 6-letter password consisting of lowercase and capital letters with at least 2 capital letters. At least 2 capital. Means at least 2 capital means 2 capital, 3 capital, 4 capital, 5 capital, or 6 capital. But this is the long way, you know. What is the short way? The short way is you find the sample space minus what? No capital minus 1 capital. Right? Do you agree with my approach? Because the upper scenario is the long way. Is the long way. Yes. So, what is my sample space here? To calculate the sample space, you should take into account that you should both use lowercase and capitals. Okay? It is possible to use 26 lowercase and 26 capitals. So what is the sample space? Yes, 1 minus complement, but it is in probability. Here, the question is not probability. It is how many ways question. So instead of subtracting from 1, here we subtract from sample space. Yes. What is the sample space here? If you can use both lowercase and capitals, yes, Mohammed. 52 power 6 is my sample space because I can use both lowercase and capitals. I have 52 letters in total. Yes, this is my sample space. Minus no capital. No capital means only lowercase. Only lowercase. So, in how many ways can you generate 6-character password with only lowercase? It is given here. 26 power 6. Yes. This is only lowercase. Yes. Lowercase case. Minus 1 capital means 1 capital plus 5 lowercase, right? For example, capital, lowercase, lowercase, lowercase, lowercase, lowercase. But is this the all? No. The first one may be a lowercase, the second one capital, lowercase, lowercase, lowercase, lowercase. And capital can be shifted 1 digit right, lowercase, lowercase, lowercase, lowercase, and so on. What is the probable, or in how many ways can you generate the first one? The first one starts with a capital. So I can use 26 capitals in the first digit times The last 5 digit is lowercase. I have also 26 lowercase power 5. Okay. Also, I have yes times 6. Why? Because lowercase, lowercase, lowercase, capital, lowercase, lowercase, lower, capital, lower, capital. We have 6 different combinations for it. So I multiply it with 6. This is the case for only one capital, okay? The place of the capital can be shifted. So it has 6 different occasions. Yes, this is the answer for the part B of the question. Do you agree with it? If okay, I will pass to the part C. Okay. Part C says a 6-letter password consisting of lowercase, capital, and digits with at least one capital letter and at least one digit. Yes. First, our sample space consists of 62 digits, 62 different combinations or characters. In total, we have 62 total characters. A 6-letter password, yes, consisting of each one can take 62 values in our sample space. At least one capital, at least one digit. Yes, this is at least one digit. This is sample. Here we can use lowercase, capitals, and digits for the sample space. Okay. I can solve, or I suggest a solution that this is sample space minus no capitals minus no digits. This is okay. This is sufficient, Mohammed. Because at least one capital means when you subtract no capitals, you satisfy this condition. Okay. Also, when you subtract no digits, you satisfy this condition also. So, what is my sample space here? My sample space is 62 power 6 because I have 62 characters minus no capital means I am using lowercase and digits 36 pardon, power 6 minus no digit means lowercase and capitals, it is 52 power 6. So This is the number of passwords that you use lower cases, capitals, and digits, including at least one capital and at least one digit. Okay? I think the solution of this question gives you the method or the how you should approach to this type of questions. If okay, let's continue. Do you have any doubts or questions about this? Okay. Conditional probability and independence. Yes, humans often have to act based on incomplete information. If your boss has looked at you gloomily, nervous, you might conclude that something is wrong with your job performance. However, if you know that she just suffered some losses in the stock market, this extra information or knowledge may change your assessment of the situation. You get relaxed. Conditional probability is a tool for dealing with additional information like this. Conditional probability is the probability of an event occurring given the knowledge that another event has just occurred. It is denoted by PA given B, probability of A given B. Here, B is the event that is just happened. We know that B is given, B has happened, okay? The right side of the line, vertical line, is the given event. And A is the probability we want to calculate or find. In the bounding box here, PA given B is formulated as PA intersection B over PB. Don't forget, denominator of the expression is the right side of the probability. The given part is the denominator. For PB greater than 0. We have also a reduced sample space approach for this type of questions. In case when all the outcomes are equally likely, it is sometimes easier to find conditional probabilities directly without having to apply this equation. If we already know that B has happened, we need only to consider outcomes in B, thus reducing our sample space to B. Yes, this acts as our sample space, and we divide number of outcomes in AB with number of outcomes in B. For example, probability that a die is 3 as a standalone event, we know that probability of a die is 3 is 1 over 6. But if it is given that a die is odd, you know, odd numbers are 1, 3, and 5. So my sample space is reduced to 3 occasions, and one of them satisfies my condition that a die is 3. So my answer for this question is 1 over 3. And probability that a die is 4 standalone is 1 over 6. But if it is given that the die is odd, yes, you see that they have no intersection. So it is 0 over 3. So it is 0. And let A be a family has 2 boys, and B, a family of 2 has at least 1 boy, 2 children here. A family of 2 children has at least 1 boy. Find PA given B. Yes. Solution. The event B contains the following outcomes. What is event B? at least one boy. Yes, at least one boy with two children means boy and girl, girl and boy. Only one of these is in A. Two boys, I mean. Yes, two boys. 1/3. However, if I know that the family has two children and I see one of the children and it is a boy, then what is the probability that they have two boys? Then the probability suddenly changes to 1/2. After you see the first one is a boy, the probability changes to 1/2. Why? Because if the other one is a boy, yes, the condition is satisfied. Yes, this is conditional probability. And independence. Yes, let me start with repeating the formulation for conditional probability. You know, it is P A given B equals to P A intersection B over PB. Yes. But if the two events A and B are independent, they have no intersection. In the case they are independent. Okay? So here, if they have no intersection, what can you say about it? A given B. No, the Venn diagram doesn't hold for this question, this situation. I started with a wrong way to explain it. Sorry, I have to delete it. I will conclude this expression to independence at the end. So sorry. Here, if you are asked probability of A given B, and you know that A and B are independent, what does it mean? It means that the extra knowledge that B has just occurred doesn't affect A. Doesn't affect event A. So I can say that this is equal to PA simply. Equal to PA. Okay? So in independent events, I can say that if two events are independent, if one of them is just given as it happened, it doesn't affect the occurrence of the second event. Yes. And here, therefore, I take this equality and replace PA for what? For PA given B. A given B. But this is when this is in case of independence. Okay. So let's reorganize the expression. Probability of A equals to probability of A intersection B over probability of B. Therefore, P A intersection B equals to PA PB in case of independence. Yes, to give an example about it, for example, you roll 2 dice. You are asked the probability that the first one is a 2, or let's say 3, and the second one is, let's assume 3. Probability of 3 is, 1 over 6. Probability of another 3 is, x equals to 3. X equals to 3 is again 1 over 6. So, if you are asked that probability of x equals to 3, x1 equals to 3, given that x2 equals to 3 equals to what? You know that the second one is 3. What is the probability that the first one is 3? It is given that the second die is 3. What is the probability that the first one is 3? Does it change? Does it affect each other? They do not affect. You roll the first die, you get a 6. And what is the probability that the second one is also a 6? They don't affect each other. So it is equal to Px1 equals to 3. And it is 1 over 6 simply. This is the case for it. Okay? I mean this. So we can conclude that probability that both two dice are x1 equals to 3 and x2 equals to 3 is what? PA times PB. 1 over 6, 1 over 6, and 1 over 36. For a coin tossed twice, denote H1, the event that we got heads on the first toss, and H2 is the heads on the second. Clearly, PH1 equals to PH2 equals to 1 over 2. Then counting the outcomes, PH1 H2 equals to 1 over 4. It is the multiplication of PH1 H2. So, therefore, H1 and H2 are independent events. You can extend this for multiple events. Probability of A1, A2, ... AK equals to probability of A1 times A2 times probability of AK. Yes, and this is our electronics or telecommunications question. What is the difference between an event independent and mutually exclusive? I think they are the same, Ahmed. I cannot see a difference between them because exclusive events have also no intersection, or occurrence of one does not affect the second one. Yes, 3 bits, 0 or 1 digits are transmitted over a noisy channel. Yes, in telecommunications, noisy channels are problems of transmitting a signal or signal, let's say. For example, you have 3 digits. Let's say they may be 101. Let's assume it is an example, okay? We have 3 bits like here over a noisy channel. We give it to the channel. What is a channel? Sometimes wireless channel, sometimes wired channel. Both channels may be noisy. Wired channels are a bit less noisy, but wireless channels may be a bit more noisy. So they will be flipped independently with probability 0.1 each. What is a flipping mean? What does it mean? Flip means, for example, 0 to 1 or 1 to 0. And probability of flipping is not no switching places, but changing the value. Okay, they don't change places, but its value can be changed. 1 to 0, 0 to 1, 1 to 0. They may change. Then probability of changing is 0.1 for each digit. And what is the probability that at least one bit is flipped? Yes. This is a probability question. Probability at least one flip equals to 1 minus what? What is the complement of this event? At least one flip means one flip, 2 flips, 3 flips. But it can be solved in a short way. 1 minus probability of what? No flip, yes. Yes. 1 minus probability of no flip. So it is 1 minus what? Probability of no flip. Flipping probability is 0.1. So non-flipping probability is 0.9. Okay. Pardon. Yes. So probability of no flip for 3 digits is 0.9 power 3. Okay. And this is part A. Part B. Exactly one bit is flipped. Exactly one bit is flipped means, for example, the first one may flip. The first bit flips, the second doesn't, the third doesn't flip. Or alternatively, the first doesn't flip, the second flips. Or the third flips, no flip, no flip, flip. We have 3 alternatives. So, what is the probability for the first one? It is flipping probability is 0.1, no flip 0.9, no flip 0.9, and we have 3 of them. Okay, this is the probability for what? 1 flip, 2 no flips, and we have 3 different expressions for it. So we multiply it with 3. Let's check if it is true. It's 1 minus 0.9 power. Second one is 3 times 0.1, 0.9 square. Yes. Okay. The lesson is recorded. Yes. I recommend you to check yourself with these self-test questions and their answers. Okay. And 3 is in conditional probability is the last page for today, I think. Yes, this is the last page for today. As you see, this is a way of representation for conditional probabilities. Suppose that we are drawing marbles from a bag that contains 7 red, and 3 green, marbles. From a bag that, yes, the drawing is without replacement. That is, after we draw the first marble, we don't put it back. Yes. Let's say that R1 means the first marble is red, R2 means the second marble is red, G1 means the first marble is green, and so on. Let's fill out the 3 representing the consecutive choices. Yes, the first marble, the probability that the first marble is red is what? 7/10. And the probability that the first marble is green is 3/10. After the first marble is red, the probability that second is green. The second is green. Given that first one is red, we don't put the red one back. So we have 3 greens, total 9 marbles. Yes. So this means probable that second one is green, given that first one is red. And given that first one is red, what is the probability that second one is also red? We have 6 remaining reds. After 7, we have 6 over 9 total. This is PR2 given R1. And if you multiply them, what do you get? That is probability that R1, R2. That means first one is red and second one is red. Means 7/10 times 6/9. That is 42/90. What does it stand for? Why did we write it? We have written it, we have stated it to show that probability of R1 times probability of R2 given R1 equals to probability R1 R2. If we reorganize it, probability of R2 given R1 equals to probability R1 R2 over probability R1. I think you remember the rule, the first rule of conditional independence, the conditional probability, that you divide intersection with probability of the given event, the right side of conditional probability, as here. So we showed it. Is it okay? That's all, friends, for this week. Do you have any question? I will share my lectures in YouTube, my YouTube channel. You can find it by writing İlker Türker probability to YouTube, okay? I had shared recently the first week, but didn't share the second and the third, but I will share them today, okay? So have a good day. Yes, the channel's name is my name. I think, I suppose that. If you write my name, İlker Türker, and probability, you can find it, okay? But there may be last year's or previous year's probability lectures also in Turkish. You should find this year's English courses, okay? Okay, see you next week.